Okay, here we go. So, today we're going to learn a new sequence and then also some new series because of that. So one new sequence formula and then two new series formulas. Okay? And we're going to talk about the named sequence geometric sequences. Okay? So, we know arithmetic. So first of all, we know a sequence. A sequence is a list of numbers, right? A sequence is a list of numbers. And then when you sum that list, when you change just the commas to pluses, right? We're adding them up. That becomes then a series, right? Then arithmetic sequences are a specific kind of sequence, right? Arithmetic sequences have a common difference. Consecutive terms have a common difference, right? They always are, different by the same amount. Okay. Geometric sequences, okay? A geometric sequence is a sequence of numbers, and this is again one that you, I believe, have seen before, where the ratio of consecutive terms is the same. So instead of finding a common difference, we'll be finding a common ratio.
So with when it's not the arithmetic sequence, but it's multiplied and instead of plus,
Yes.
that is would there be a difference of a quotient?
In a sense, yeah. So remember, a ratio is a number divided by a number, right? A number over number. So in a sense, that's like a division too, or a quotient, you could say. Yep. So let's take a look here at an example geometric sequence. Okay. So 2, 6, 18, 54, ... Okay. What's the pattern here? What's happening every time with these terms? Multiplying by 3. Okay. The other way we could think about that, right? So yeah, it's times 3 here. So again, you could also talk about this common ratio idea. So for example, if I take my term 6 there and I divide it by the previous term, it's 2, right? That's going to be the same as 18 divided by 6, which is the same as 54 divided by 18. They all equal 3. So then that makes 3 our common ratio. Okay? Or as Grant said, we're just multiplying by 3 every time. So obviously, if you can see that we're just multiplying by 3 every time, just go ahead and say that's your common ratio. Okay? It's whatever you're multiplying by every time. Okay? But of course, if you can't figure it out, just take your next term divided by your previous term, and then check to make sure that kind of fits with the rest of it. Okay? It's kind of important to be able to do that because we have things like, things like this. Okay. What's our common ratio going to be here? 1/2. 1/2, right. So fractions. Okay, but again, if you're looking at this, you're it's going down, but I'm not really sure how. Just take your next term, divide it by your previous term. And it all will equal 1/2. Okay, it will all equal 1/2 there. Right. For the formula for the nth term of a sequence, so nth term of a geometric sequence, okay, it's going to be, well, of course, a sub n equals, for the nth term, okay. Oh, go back up, sorry. Right there. Okay. It's going to be the a sub n, nth term. Of course, we need to start with our first term, right? Because that's kind of like what we do with our Other problems there? Right? Want to know where the first term is? And then to find that nth term, well, we're going to start again with like, the 2 or the 24 there, that first term, and then we're going to multiply. In the first pattern, we're going to keep multiplying by 3, so times 3, times 3, times 3. Here we're going to be multiplying by 1/2, times 1/2, times 1/2, times 1/2, times 1/2. Right? And we're going to do it so many times until we get to that nth term. So how do we represent repeated multiplication in math? What do we use to represent repeated multiplication? Exponents, right? It's going to be exponents, powers. And so we're going to have our common ratio r to the n minus 1 power. And just like in the arithmetic sequence formula, we have that n minus 1. We also have the n minus 1 here in our geometric sequence formula. Again, because the idea is we start with counting. Our first term is counts as like the 0 term in a sense. So we have to kind of like account. We're going to go out. If we start at the first term, we would go out to the 100th term. That means we need to go 99 more terms out. Okay, because we're already we start at the first term. Okay, so that's why we have to go 99 more terms out. Okay. So, let's just do a quick example with that, and I'll give you guys one to try then. Let's write out the formula for the geometric series, sequence, sorry. See, I always do this now. Write out the formula for the geometric sequence. Given a sub 1 is 3 and r equals 2, then write the first 5 terms. Okay. I don't know. And again, why 5 terms? Who knows? It's not like there's any sort of magic behind the 5th term there, but I guess it kind of gives you enough where it doesn't become too redundant, maybe. I don't know. Okay. So we'll write the formula out here first. So again, our formula is a sub n equals a sub 1 parentheses common ratio to the n minus 1 power here. Okay. And so for our purposes, the first term there, right, is 3. Common ratio, we're told, is 2. And to the n minus 1. So we'll find the first 5 terms. So a sub 1 will be 3 times 2 to the 1 minus 1, so 2 to the 0, so it's just going to be 3. But that makes sense, right? We were already told that the first term was 3 right there. And so then a sub 2 will be 3 times 2 to the 2 minus 1. And so then that'll be 2 minus 1 is 1, 2 to the 1 is 2, times 3 will be 6. And then so on and so forth. I mean, I could keep using the formula, but I also just know we're going to be multiplying by 3 every time. So it's going to be 3, then 6, then 18, then 54, and then 162. I think they're right.
Yeah, that's right.
I'm sorry, yep. Oh, I made an error in my calculations here, didn't I? Yes. It should be 3. It's so easy that I made an error. Yeah. 1, 2, 3, 4, 5. Yeah. I knew that. No, I didn't. All right, so there it is. Fixed it. Fixed it. Okay. Fixed it. All right, questions on that? Straightforward enough for you? Okay, so then, for you to try, find the 15th term of the geometric sequence whose first term is 20 and r equals 1.05. Okay. Go ahead, give that one a try there. Let me see how you typed it in. Let me show me what you typed in. Oh, 1.05. That's why. Looking good. That's what we got over there. 39.6. Yep, looking good. Good. I did pretty other places, but I mean, if we did one, that's fine.
But the best thing about it is if you go on like a interstate, like not an interstate, but just a normal highway, and there's like no way else. Merging was so easy. Yeah, it'll be after dark. But you gotta be careful because sometimes the exits can be really janky on other highways. You can use your brakes. I love her.
39.599. We're good? Shh. Look good.
She's great.
What's that? 596. Then, of course, we can take these sequences and add them up, right? All right?
Why would we do that?
Because we can, and because that's what we're asked to do. Okay, so remember that yesterday, right, when we talked about sequences, with arithmetic sequences, we then said, okay, we're going to add these things up, okay? And of course, like yesterday, if you remember, I was like, we kind of, when we're adding up an arithmetic sequence, when we add it up for the arithmetic series, okay, we need to have a finite number of numbers that we're adding up, right? Because an arithmetic series, right, if you add up an infinite number of things, it will go either to positive infinity or negative infinity, okay? Because it's going to keep, the numbers are going to keep getting bigger. Even if your arithmetic sequence, you know, or starts at something like, I don't know, 0.001, and you add, you know, like one billionth every time, eventually it's going to go to positive infinity or negative infinity.
But like infinity doesn't always mean like the largest thing. It can also, like pi technically goes on to it.
correct, but the value, I mean, you would definitely say that infinity is larger than pi, though, for example.
Would you? Because
I think so.
but like pi is also a type of
I would say, right, pi is like not,
there are things larger than
I don't know. I mean, I hear what you're saying. Pi, I see what you're saying, is in like pi is not like as definite as other numbers are, like 2 or 3 or something like that, for sure. And infinity is also not definite in the same sense that other numbers are, okay? But my point is because, and especially with like now, because we're counting numbers, pi wouldn't be what you count by, right? We count by whole numbers. But infinity, a whole number still can go to infinity and stuff like that. So the sum, right, and my point with the arithmetic series there is that if you do an infinite arithmetic series, you're going to end up with either positive infinity or negative infinity. It's just going to happen eventually because you're going to be adding by the same amount each time or subtracting by the same amount each time and then combining those things together. Okay? Now, geometric, we have also a finite geometric series formula. Okay, so arithmetic has a finite arithmetic series formula because you can find the sum of a finite number of things for an arithmetic series. Same thing for geometric. I don't have the story like I did for Gauss, okay, yesterday. I'm just going to give you the formula here. And again, you will be given the formula, but you'll need to know how to use it. Okay. So, of course, S stands for sum. A sub 1 is the first term. Okay. R stands for the common ratio. Okay. Maybe I should put S sub n for the sum of n terms. Okay. And then n stands for the number of terms, right, in that series. Okay. Now, comparing this or contrasting this with our finite series formula for arithmetic, okay, so our finite arithmetic series formula, you'll notice some differences, okay? Well, actually, let's look at the similarities, right? You still need to know the first term, right? You still have to know a sub 1. You still need to know your common ratio in this case, just like in the arithmetic one, you have to know your common difference, right? You need to know the number of terms, just like you do in the arithmetic series. But what you don't need to know is the last term, right? You don't need to know the final term in your series here. You just need to know the first one, and then the number of terms and your common ratio, and that's it. Okay. The biggest thing that students run into difficulty here, besides first of all deciding which formula they're supposed to use and stuff like that, the biggest difficulty students run into is typing this into their calculator correctly. Okay, that's probably the biggest difficolty I would see.
Do you do it bit by bit or all at once?
You can do it all at once. I just recommend you use a healthy dose of parentheses. So parentheses around the numerator, parentheses around the denominator, especially. All right. So let's take a look at an example, and we'll see how good we all are at this. All right. We'll do 2 maybe, or I'll do 1, and then you guys can try 1. Sigma notation, it's back. We were afraid it had gone away forever, right? Okay. So, again, my encouragement to you here is that you write out the first couple of terms, okay? So let's do that. The first term is going to start with n equals 1, so we'll have 0.3 to the 1 or just 0.3. Okay. Then we'll add to that the next term, so it'll be n equals 2, it'll be 0.3 to the 2, right, squared, and then 0.3 to the third, and then you get the idea, right, plus dot, 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 and then plus 0.3 to the 8th. Okay. So we first of all have to decide here, what kind of series is this? Is it arithmetic or geometric? Is it arithmetic? So what are we adding by? What's the same amount we're adding by every time here? Or subtracting by every time here?
We know what the end is.
Okay, so is it arithmetic then? No. It's geometric, okay? How do we know it's geometric? What's the number that we continue to multiply by for each new term? We multiply by what? Another 0.3, right? This is 0.3 to the first. Then we have 0.3 squared, so it's going to be times another 0.3, right? Then times another 0.3 gives us 0.3 cubed, and then times another 0.3, times another 0.3, times another. So this is like times, right? Times a 0.3 every time here. Does that make sense?
Well, if you're timesing it by 0.3, wouldn't that make that?
Remember, arithmetic, we are adding by the same amount for each term. So term 1, what's that?
It has to be added.
Yes.
Oh, okay.
Yes. Arithmetic, a common difference. So that means you're between your two terms. If you take this term and subtract it, it should be the same as the difference between this term and this term. But it won't be the case here, right? It's a common ratio or common quotient, if you want to say something like that. Okay? So yes, very clearly we are geometric. Are we finite geometric?
Yes.
How can we tell this is a finite sum?
There's an 8.
Right, we stop, right? We have to count up to 8 there, okay? So it is finite geometric series. We're going to use this formula right here. Now, of course, there's only 8 terms here, so if you wanted to just like brute force it, you could, okay? You could just kind of like find every term and add them up. That's one way to do it, okay? But let's use the formula because we've got it. So the formula here will be S sub 8, I guess we'll say here. All right, the sum of the first 8 terms. First term is 0.3 times, and then 1 minus 0.3 to the 8th over 1 minus 0.3. Okay, and now I would strongly encourage you guys to get your calculators out, type this in, make sure that you type it in correctly. Okay. And again, I would just recommend a healthy dose of parentheses. Okay, especially around the numerator and the denominator separately. Okay, so parentheses for the numerator, parentheses for the denominator. Your end goal should be 0.429. Okay, so if you type it in your calculator correctly, you should get 0.429. Okay, here's how I type things in if you're looking for, something to consider. So I would say that's and that's fine. If you want to do bit by bit, that's your choice too. Okay. I would say there's like the bare minimum what you need to type in. I would say, I don't know if there's any more efficient way to do it than that. Okay, bare minimum, parentheses on the numerator, parentheses on the denominator. Okay.
Wait,
You got it. Gesundheit. Huzzah. Okay, we're good? Yes? Everyone got that? Feeling confident? Good, because, we're not feeling confident. Well, I'm going to have you do it anyway. So here, you guys try this one. Time to fly, baby birds. Time to fly. Okay, there you go. Try and find that sum there, please. From 1 to 12 of 4 times 3 to the n minus 1. The sum from n equals 1 to 12 of the terms there, 4 to the n minus 1. Okay? Now, of course, come test or quiz time, right? These problems will not be in the context of geometric series or arithmetic series. So in other words, I'm just going to throw a problem at you. I'm not going to prompt you with the fact that, oh, by the way, we've been doing a bunch of notes on geometric sequences and series, so this is probably a geometric sequence or series. You need to be able to identify and discriminate between arithmetic and geometric. Okay, so that's where writing out the first couple of terms can help you figure out which one is, what kind of pattern this is.
Basically, you can give us number 1 could be arithmetic, number 2 could be geometric.
Exactly, they'll be mixed up, and the direction will just be find these sums or evaluate. Really, is all I have to do here is just say evaluate.
How do you determine it again?
How do you determine what?
Are there any telltale signs?
Absolutely. If you write the first couple of terms and you just look at what's the pattern from term to term.
First,
Do you have to do that first? No, I would say not. So if you think about in arithmetic, what are we doing? We are repeatedly adding the same amount each time. In mathematics, what operation do we use to do repeated addition? Multiplication. So if in your series you see your n term as being like it's a number times n, so 4 times n or 3 times n.
This is, but to the exponent means repeated.
Repeated multiplication, which is what geometric is, right?
Alright, cool.
Large. Yes, it will be large. It didn't overflow your calculator though, right?
No.
Okay, that's good because that happens sometimes in these problems. Didn't write an answer down for myself. That's annoying. All right. Okay, do we get 1,062,800? 80?
I'm sorry.
Around 80. Okay. 1,062,880. But we're not done yet. Okay, there's one more formula that I'm going to be giving you guys. Hold up. Next divided by previous. Next divided by previous. Okay. Believe it or not, with geometric series, there are particular geometric series in which you can add up an infinite number of things and the sum will be finite.
Why?
Okay, so there are, well, I'm going to show you here in a second, okay? So, or I'll give you the formula. The why, that's going to be tricky, but I can kind of explain it, okay? And you can see if you buy it or not, kind of thing. But so again, for our arithmetic series, right, we can only add up a finite number of things for an arithmetic series. Either that pattern will, get larger and larger and larger, so that we're going to go towards infinity as we add them up, or it'll get smaller and smaller, or more and more negative, and so we'll get closer and closer to negative infinity then when we add them up an infinite number of times. Okay. Of course, finite geometric series makes sense because now when we're doing geometric series, we're multiplying by the same amount each time, and you can see that after just like 12 terms here, we're already very large, and of course, if we kept going, it would be even greater. If we went to infinity, certainly that would go off to infinity, kind of thing. So, yes, Ro.
How come the the n minus 1 is like how that doesn't affect the geometric sequence equation thing.
Because it has to do with the number of the terms, I would say. It just has to do with the number of the terms there, so there's going to be 12. And in our formula is the number of the terms, so there's going to be 12 terms there.
But it's n minus 1, so
Mhm.
it's not 11.
I see what you're saying, but I think it's
Because in the one above it, it was just n, and then
right.
so it kept it.
Correct, but I think it would only, that n minus 1, I mean, it does affect things, I'll say, but it affects things in that if it wasn't n minus 1, that would just change the first term, and so that would just change then this number. We still are going to have 12 terms, so we use the 12 in for the n there and here. Okay.
It just
So,
happens to be 4.
because of the calculation, the way it's set up.
Or else it would be 1.
Mm-hmm. Or else it would be 1. Yes? I think? Or I mean, like, if it was just n, you mean? It would be a different starting term, and so then you'd have a different 12 there, and then it'd be a different final sum kind of thing. But you still would have 12 terms. Okay. That being said, though, with an infinite geometric series, that means we are able, okay, to find, for example, a sum of an infinite number of things, and the answer, the sum of an infinite number of things, will be finite. Why is that the case? Well, if you can imagine here, because of the nature of infinite geometric series, okay, we're repeatedly multiplying by the same amount each time. Imagine if you're taking your number and multiplying by, say, 1/2 every time, like we saw earlier, and well, it's on the other page there. I'm not going to give it out. But if we multiply by 1/2 every time, we are shrinking those numbers that we're adding by pretty significantly, right? You keep having and having and having and having. Eventually you will kind of be stuck into like I don't know, like a I don't even know what to say there. If you keep having things, it will get so small, so infinitesimally small that you're adding by every time that you're going to have this kind of upper limit to it. You could think of it as like this, like if I were to walk to the door, right? If we measure the distance from me to the door, okay, and I only ever walked halfway to the door every time. So I'm adding on, whatever half my distance is. So let's just say, for argument here, it's like 20 feet, right? So if I walk halfway for the first time, so that's 10 feet, that'd be my first term, be 10. And I would add 5 feet on for the next thing. It's okay. It's okay, phone. And then 2.5, and then 1.75, right? Or no, 1.75. And so on and so forth. I keep adding half and half and half, okay, to my distance to the door there. Am I ever going to get to the door?
No.
The answer is no, but I'm going to get so close that we'll say, okay, you get to the door essentially, but I will certainly never go beyond the door, right? That's kind of the idea here, okay? So for an infinite geometric series, okay, and this is actually a formula that you will use if you go on to Calculus ABBC. You'll actually use this formula again in Calc BC, Calc 2, okay? The formula is the sum of an infinite number of terms there is the first term divided by 1 minus r. Now, obviously, there are going to be stipulations here, right? Because if instead of me walking halfway to the door every time, if I walked to the door twice as much my distance every time, well, I guess that'd be kind of weird because then but anyway, if I like doubled how much I walked every time, I'd be walking an infinite distance, eventually kind of thing, because it would just be so far that I'm going, okay? So we have to stipulate how the size of our r, okay? How do you think we need to stipulate size for r here? What limitations do we put on our common ratio? We should only be multiplying by what every time here? What do you think there, Grant? A number less than 1, but of course greater than 0, right? Mm-hmm. Yep. And so for our cases, we'll just say absolute value of r is less than 1, and of course r not equal to 0, because a 0 is not really a sequence anyway, right? Okay. So otherwise, the sum would approach plus or minus infinity, again, depending on the values. Okay? Plus or minus infinity there. Okay?
Because like when r is in that's why
Mm-hmm.
that's why it's like r is moved after that.
Correct. And well, that just counts because we could also, like for example, so if r is negative 1/2, that means that it would be you could find the sum of that infinite geometric series.
But if it were not,
Correct. If r was equal to negative 2, that infinite series, geometric series, would not converge. We say, okay. So this is very special. Not only can we say that an infinite sum, okay, does not go into infinity, we can actually say what sum it goes to, and that's very unique, okay? Later in calculus, you'll learn techniques, if you take ABBC, you'll learn techniques for finding the sum of an infinite number of things, and you'll be able to maybe say that whether it diverges, that is it goes to infinity, or converges, that means it goes to a finite number, but it's even more special that we can actually find the sum of an infinite number of things. Okay, that's very unique. Only, again, a few situations where this happens, such as an infinite geometric series. All right, so let's evaluate, just as an example here, the sum from n equals 1 to infinity of 500 times 3/5 to the n minus 1. So here's how we designated infinite sum. Okay, we put infinity at the top of our sigma there. So we're going to be adding up an infinite number of things. Okay, again, my encouragement to you, write out the first couple terms here. So the very first term will be 500. Okay, and then 3/5 of 500. I guess I might as well just go ahead and do it this way, just to make it. What is our common ratio here? What are we multiplying by every time? 3/5. Okay. So does that allow us to find this infinite sum then? Yes. Okay. So again, if you were trying to do an infinite sum here and it's had something that was greater than 1, right? So if this said like 10, for example, here, if you found that your common ratio was 10, and you're trying to find an infinite number of things, you would say the sum does not exist. Okay. It diverges, if you want to say it that way. Okay, but here this sum will exist because of that 3/5. The absolute value of 3/5 is less than 1. Okay, how can we find it? Well, we'll just do the sum of an infinite number of things there. The first term is 500, and we'll divide it by 1 minus our common ratio of 3/5. Again, be careful how you type this in your calculator. Okay, use a healthy dose of parentheses. So bare minimum, you want to look like you can write something like that, and your calculator will be okay with that. Excuse me. So the answer here is 1,250. Okay. So the sum of this infinite number of things, starting at 500, is 1,250. Alrighty. Questions on any of this? All right. Then, page 667. Numbers. 7 to 19. 23. 35. 37, 45, 49, 67, 77, 83, 93 to 101.
Oh my god.
Odds. Yeah, one second. And it's all
Those are
calculator
all
active.
odds. Oh, never mind. I didn't realize there were like dashes.
Okay, there's your assignment. Sorry, okay. So yes, Caitlin, you said you wanted to come in, right?
Yeah, to take the
For the bonus quiz, okay. Row as well. And Jenna, yes, you. Jenna, you.
So it's only law of sciences.
Correct.
Nothing else. I want to come in.
Correct.
Okay.
Maddie G. Well, I'll say you don't have to use law of sines and law of cosines for all the problems, but you may use law of sines.
What does that mean?
Don't you have to use?
What's that? Not always. You were able to solve triangles before law of sines, law of cosines.
Oh, by the way, that E thing, that's on Minnesota.
Sigma?
I guess. I was like, four.
The E thing. Any other set requests?
Oh, the sigma thing?
Yeah. Yeah, I know, right?
It's clearly sigma, right?
Right.
Just kidding. I
I
don't know. How
See,
that.
whenever I don't know what it is, I always get
What?
sick.
Oh no.
CA calculator active?
Yeah.
It's my favorite number. One time I guessed my favorite number because I didn't know what it was on the SAT, and I went back because I had extra time to try and figure it out, and the answer was 7. It was amazing. I told my friends, and they were like,
How do you, what program are you using?
I don't know, some random.
Okay, it's just
Let me see what that
So Google maybe.
Yeah, but then turned real bad.
A good thing that is a good app for
She was
things
already
like that
all
on your phone or on your anything. It's free, and yeah, there's this one app. It's called Autodesk. It's Autodesk.
I know, like Evernote is a popular one.
On my iPad, and if you make an account, then you get all of the
Here.
features for free because it got.
It's not that, it's just not that. It's not.
So what is it, like making a PDF or something?
Yeah, you gotta use something with like a silicone on it. Doesn't-
Yeah.
Usually average vary depending on how many people take it at a time.
I think it's Autodesk Sketchbook.
There are other factors.
Yeah, Autodesk Sketchbook.
Yeah, anything like that.
And it's free.
Nope, nope, nope.
Less science and
All right, let me
You can use it without Wi-Fi.
cut the video here.
Resolution. That's per inch.
Yes.